Hi, my name's Alta, and AK Amin and I are going to present our project on CNN for CT segmentation. So by way of introduction, cardiovascular diseases are the leading cause of death globally, but early diagnosis and treatment can reduce mortality. A non-invasive method for characterizing the structure and function of the cardiovascular system is a cardiac CT, and this can lead to improvements in both diagnosis, monitoring, treatment, and prognosis. As we can see on the right, ventricular volumes, ejection fractions, and myocardial mass are all useful parameters that we can obtain via a CT segmentation. So what is a segmentation? Well, it's really just a labeled division of the heart into its anatomic regions. And we need accurate labels to get accurate measurements, but this requires specialist knowledge of the cardiac anatomy and hours of manual labor to create these segmentations. So CNNs have promise as an automated technique for creating these.
The standard CNN used in biomedical imaging for image segmentation and classification is called the unit, and that's mainly because of its architecture, where you have convolution layers fed with pooling layers that shrink the model, and then from there you expand with upscaling layers and more convolution layers that use information from the previous layers. What does that really mean? Well, similar to how when we have an image that is a convolution of a point spread function over an object, here, in this case, we're using a convolution filter as the point spread function and the image as the object. So the image is having a convolution filter, such as G, flipping around, going through, multiplying and integrating across to create a convolution layer. And from there, we pick the most salient information in that convolution layer through the pooling layers and downsample it of just the most important information. From there, repeat that process again until a point where we start upscaling from the convolutions that have been downscaled, and we upscale by information from the previous convolutions and previous layers until we eventually reach back and inverse convolute our way into the original image, this time with information that can allow us to segment structures that were most saliently identified based on what our interest was.
So our project set out to tackle the problem of what happens when you have a small data set and not very many segmentations, and you want to train an effective network. Well, because manual segmentation is slow, it would be nice to have a neural network segment images for us. And we want to know what matters most when you have a small data set and what properties of the images in the input result in the most accurate labels. And we are going to compare here image resolution and image augmentation. So for our model, we started with 200 labeled CTs that are 512 by 512 by varying Z directions. And we initially started with a normalization of the pixel intensities, but found that because there were some high intensity artifacts, we needed to apply a thresholding to remove those so that the rest of the values made the image visible. So after we applied the thresholding, we then went to a normalization and downsampled the images for computational purposes. This gave us two data sets, a 64 by 64 by 64 data set and a 128 by 128 by 64 data set. Each of these were split then into 75% training, 15% validation, and 10% testing. And it's important to note that we actually tried two test data sets for each of these. One test set that's the original 20, and another set that's 40 images with contrast augmentation applied to the original 20. So for each data set, then we applied augmentations or no augmentations. The augmentations are a flip, a rotate, and contrast, which AK will talk about. And we ended up training 4 models, 2 at each resolution with and without augmentations. The training parameters here were consistent across all of the models, with the exception of batch size, which we had to reduce for the larger data sets.
Like Alta mentioned in the last slide, these are the augmentations that we applied. On the top left, you can see what the original image and the original label look like. And then we flipped, rotated, or contrasted each data set. We actually did all of them, but individually, no augmentation was applied on top of each other. We did the rotation and flipping for anatomical reasons. Some patients have situs inversus, so it's possible that you might end up with a patient whose heart or organs are pointing in the opposite direction. So we did a binary flip. And then we rotated because the the base to apex axis of a patient's heart can be slightly different. So we did random rotations between 20 and negative 20 degrees with increments of 5 to account for that. And then the contrasting we did for more CT reasons. Like we were mentioning before, we noticed that we had some really high intensity artifacts and we thresholded them out. But in a similar vein, there's also differences in dynamic range between data sets. So we randomly took off parts of the top of the range and top parts at the bottom and then renormalized after that. And you can see results of what that contrast would look like. On the bottom right, you can see what the same image that's on the top left looks like after it's been randomly contrasted. These are this is an example result of the 64 data set where the top row is no augmentations and the bottom row is with augmentations. And the far right column is our model's predictions. The runtimes are about 45 minutes for no augmentations and about 2.5 hours for with augmentations. And at baseline for 64 with no augmentations, you can see that our model learned the chambers. And at this point, what we're trying to optimize for is how well we can learn the chambers. And so with augmentations, it did improve performance, you can see visually. And Amin is going to later on talk about the actual data. Here's an example of what the 128 data set looked like. Again, no augmentations on the top, with augmentations on the bottom. The runtimes are about 5 hours and 12 hours, so significantly longer. But you can see, importantly, that they were longer, but the data looks much better. The original images look much clearer, and as a result, the segmentations also look clearer. And Amin is now going to talk about the actual data.
So when evaluating our data, we ran it into both a augmented, which is contrasted data, as well as normal data at 2 different resolutions. Here we can see the 64 resolution data being fed into a model trained on 64 resolution images that were both augmented here on the left, showing in more pastel colors, or not augmented training, shown on the right in more darker colors. As we can see, statistical significant difference in distribution of the dice scores, which are essentially a measure of the overlap of the prediction as well as the actual image. And the model was able to gain performance based on augmented training. However, that performance statistical significance is lost when we feed in more actual contrasted data. At higher resolution, similarly, feeding in 124 resolution data, we don't see a statistically significant gain, but in fact, a statistically significant loss on a model that was trained with augmented data. And in fact, the model trained with higher resolution data, not augmented, outperforms. And similarly, even with contrasted data, the higher resolution trained model outperforms the contrast augmented trained model. Overall, the conclusion is that higher resolution is much more important when we have a low data set. And when we compare the 2 models trained on normal data at 2 different resolutions, we can see on the left is the higher resolution data has outperformed the model trained on lower resolution data.
So the key takeaway from our presentation is that image resolution matters the most. In the context of our problem, we're trying to figure out what properties of a data set we should optimize for so that we can improve the model, given that we have a small data set. And it seems that image resolution matters more than potentially doing augmentations in a lower resolution data set. Possible next steps are to see if other augmentations are more useful, for example, random or physiologic deformation fields. And then interesting applications could be training on data sets where everything is partially labeled, for example, where end diastolic and end systolic time points are labeled, and then train it to fill in the rest of the data set in order to make a robust ground truth and see how that performs, which is slightly different because we're optimizing for overfitting. But yeah, the key takeaway is that image resolution matters the most. Thanks for listening to our presentation.